Hello, everybody, and welcome to our introduction of how the sky changes on daily and annual cycles. So we've already talked about the sky as in a static sense, and we're going to go outside and we're going to observe it from our local perspective. And then we even talked about the celestial sphere, which gave us a coordinate system that fixed the stars to this concept called the celestial sphere and gave every object in the sky, or at least every star in the sky, its own unique address. Our next lesson is how is the sky changing? What is causing the sun to rise in the east, set in the west? If we're looking to the south, why is it that the stars rise in the east and set in the west? If we look to the north, what kind of motion do we see with the stars? So whenever we're talking about the changes that we see in the sky, we have two big motions related to Earth that we need to talk about. The first one, and you can see an example of this on the slide, sorry about that, is Earth's rotation. So Earth spins about its rotation axis. That's the imaginary line that goes through the South Pole, through the center of the Earth, and then out the North Pole. And Earth just spins around on this axis once per day. So our view of what part of the sky we're seeing is constantly changing as we rotate around on the Earth. And then that's going to, of course, give us our daily and our nightly cycles. So these are what we call diurnal cycles. So this is going to be the first one that we talk about is Earth's rotation. And then the second one we're going to talk about, the other really important motion of the Earth that gives us a annual change in the sky, which really tells us what constellations are going to be up what time of year. And whenever we're talking about the constellations being up, of course, we're talking about what we can see at night. And what constellations we can see depends on Earth's revolution, its orbital motion around the sun. So you can see this little animated graphic that we have going on here. And really, as the Earth is going around the sun about once per year, the night side of the Earth is pointing at a different part of the celestial sphere. So as the months tick by, we are seeing a different part of the celestial sphere, which means that we see new constellations rise, old constellations set, and this nice slow progression of the changes in the sky. The previous slide was sort of giving you a look at the Earth itself. Now I want to step back and go to our orbital view. So you got to use that visual spatial reasoning. So now we're going to be looking down on the North Pole of the Earth. The Earth's going to be rotating counterclockwise, and it's going to be orbiting the sun counterclockwise. Just for some reference, I have put Earth's orbit here, and here you can actually see the Earth itself. I marked the night side of the sky and the day side of the sky. So the day side is always going to be pointed towards the sun. And then just to help you visualize this, I've added a few stars up there. So Earth's rotation, whenever we take a look at this, is Earth just spinning around on its rotation axis. So this is going to give us our daily motions in the sky, the diurnal motions of the sky, if you want to use a more formal term. So as this Earth rotates around and around and around, you can imagine yourself here on the Earth. The green line is representing our horizon. This purple line is pointing towards your local zenith. You can also think about it as your meridian here. So as we rotate around and around and around, what is above our horizon on the purple side of what's on the purple side of the line is constantly changing. So that's going to cause the daily rising of the sun, the daily rising of the stars, the daily setting of the sun, the daily setting of the stars. Now, if we take a space-based perspective, looking at an orbital diagram for Earth's revolution, remember, revolution is Earth's orbital motion around the sun. So we're now going to watch the Earth orbit around the sun. Again, I've marked the night side and the day side. So the stars that you can see at night are always going to be on this night side. So I'm going to not deal with the rotation of the Earth. We're going to pretend as if we're going outside at true midnight, night after night after night over the entire course of a year. And then that way, we're always going to be standing at the base of this purple line. The sun's going to be on the opposite side of the Earth. So you can get a really nice view of what we would see at midnight. So over the course of the year, the Earth orbits around the sun. This Earth revolves around the sun. So you can see which stars are on the night side are constantly changing as the Earth makes its orbital motion around the sun. So these stars are viewable at night. Now these stars are viewable at night. These stars are now viewable at night. These stars are viewable at night. And that repeats on an annual cycle. So these create our annual motions in the sky. Now I want to give you a little bit more detail, and I want to give you a little bit of a stellarium demonstration of what all of this looks like. So a true Earth-based perspective. But before we do that, I want to go ahead and prime you a little bit on one of the most simple things that you've probably known for quite a long time, that the sun rises in the east and sets in the west. But what we're going to do is we are going to add in some of the vocabulary that we learned that relates to our local sky. So if we use our horizontal coordinates, our altitude, so how high up in the sky from 0 to 90 degrees, and azimuth, how far away from north, wrapping around 360 degrees, such that north is 0 azimuth, east is 90 azimuth, south is 180 degrees azimuth, west is 270 degrees azimuth, and then it goes back to north. So let's now look at the annual or the daily motion of the sun as it traverses in the sky. No surprise that the sun is going to rise in the eastern part of the sky, and then it's going to increase in altitude and increase in azimuth as it approaches due south. So this purple line, if we're looking due south, the line that goes through from due south through your zenith and then connect back to due north, is our meridian. So we're going to watch the sun rise, and it gets higher and higher and higher, increases in altitude until it reaches its halfway point, where it spent half of its time in the sky. And that happens whenever the sun is located due south and the sun is centered on the meridian. We call this meridian crossing a culmination. So we would say that the sun is at culmination. Another way to say this is that the sun is on the meridian. And another way to say this is you are at solar noon in time if you look due south and the sun is centered on the meridian. So this is the point where it'll be maximum altitude. So as it sets in the western part of the sky, it's going to decrease in altitude, but still continue to increase in azimuth because it's been moving from east to west consistently. So the altitude gets lower and lower and lower as the azimuth approaches due west or close to due west, and then the sun will set in the west. Now, one of the things I want you to walk away with this is this idea of solar noon. When the sun is on the meridian, that is what we define as solar noon. Prior to us having clocks that could keep time for us, this is how people mark time. You could always go outside, wait for the sun to be on the meridian. So if you could locate due south, just wait for the sun to be due south, its highest point in the sky, and then you know that you're at solar noon. So I could communicate to you, hey, let's meet up tomorrow at solar noon. We wouldn't be calling it solar noon, we would just call it noon at that time. And just as a fun little added bonus, now you can actually understand the origins of AM and PM. If you've ever wondered why the morning hours are AM and the evening hours are PM, it actually comes down to the sun and keeping track of time. And AM literally stands for anti-meridian, before the meridian crossing. So AM is before noon, before the sun crosses the meridian, and PM is post-meridian, so after the sun has crossed the meridian, after noon. And that's where the origins of AM and PM come. So what I want to do now is I want to go ahead and show you a quick little demonstration of what these daily motions look like using stellarium. So now I've brought up stellarium. I have this set up to be at the spring equinox just before sunrise. So this purple line right here is my meridian. Notice that goes through due south and it's going up towards directly overhead. So I'm just going to pan my view over towards the east. You can see the sun's about to rise, and I'm just going to get time moving. And I'm going to speed it up a little bit so we can watch the sun rise in the east. Perhaps a little bit faster. So we can watch the sun rise in the east, and notice that it's increasing in altitude and increasing in azimuth. So here it comes. I will add the azimuthal grid. I'm going to do my best to pause it just as it gets to solar noon. That would be whenever it's crossing the meridian and it's at its highest altitude. Close. So there we go. We are at solar noon, and now it's going to move over and set towards the west. Just because it's a little bit confusing, I'll remove the azimuthal grid whenever it's halfway on its journey to setting. And I chose the equinox because that is when the sun will set due west. It's also when the sun will rise due east. In the winter months, it'll rise a little bit south of east and set a little bit south of west. In the summer months, it'll rise a little bit north of east and set a little bit north of west. So now the sun's going to set, and we're going to see that the motion of the stars, or at least when you're looking south, matches the motions of the sun. So we're going to see stars rising over here in the east. Then we go ahead and remove the azimuthal grid. Put up some constellation lines so you can see the constellations moving. So they're rising, reaching their highest point. When they cross the meridian, that is that star's culmination. And they set in the west. So no real surprises there. But what happens if we look at the northern sky? So I'm going to pan around, and this is where you can start getting a sense of the celestial sphere. We've gone to a new sunrise. Just for this demo, I'm going to go ahead and get rid of the atmosphere. So if we look to the northern sky, we see some interesting motion. Right here is our North Star, Polaris, and it looks like everything is circling around Polaris. So if I bring up my equatorial grid, my right ascension and declination, here's the North Celestial Pole, and everything seems to be rotating around the North Celestial Pole. Now notice some stars never rise or never set. So this star right here is always above our horizon here in Knoxville. Even if I speed up time, all it does is rotate around and around and around the pole. We call these circumpolar stars because they are just circling the poles. So whenever we look towards the northern sky, our motions for our stars are a little bit different than they are for looking at the southern sky. We have some stars that never rise or never set. They just appear to circle the pole. And those are called circumpolar stars. And let me go ahead and just get that demo going one more time. I'll speed up the time. We'll go to this star right here. Get it moving nice and fast. So you can see it just circles around and around the pole. Now, if you have been a clever observer right here, you might have noticed that the altitude of Polaris is right around 36 degrees north. It's not quite exactly at the North Celestial Pole, but it's very, very close. You have to remember that the altitude of Polaris is equal to our latitude. And here in Knoxville, it's at 36 degrees north. So this is at altitude 36. It's at declination 90. But with altitude 36, that means I can move down 36 degrees to my northern horizon. So if I'm going to move down that 36 degrees from 90 degrees of declination, then 90 minus 36, the northern horizon sits at plus 54. So any star with a declination of 54 plus 54 to 90 will be a circumpolar star here in Knoxville, Tennessee. Those are the stars I'll just circle around the pole. All right, so now that we're all sufficiently dizzy, let me go ahead and stop that. And I want to just bring up my presentation just one last time and go ahead and summarize and get you oriented to what I have in the textbook slides, because I talked through a lot of the concepts. If you want to go review them, I have a slide about the stars' daily motion, where I talk about them rising in the east, setting in the west. Or if you're looking towards the northern sky, or at least if you're in, or the southern sky, if you're in the northern hemisphere, then we'll see our circumpolar stars in our northern skies. It's the opposite if you're in the southern hemisphere. And then I have a slide, so just in case all of that circumpolar stuff felt like it was coming at you pretty fast, then you can always go visit my circumpolar slide where I walk you through, and I even tell you how to calculate the declination of circumpolar stars. So all stars in Knoxville that are between plus 54 and 90 degrees of declination are circumpolar stars. I hope you've enjoyed this sort of brief introduction to the motions that we see on the sky on a daily cycle and an annual cycle. The future videos are going to go into each one of these into a little bit more depth, but I just want to get you used to Earth's revolution and Earth's rotation. Again, the revolution being its orbit around the sun, and its rotation being it spinning around and around on its rotation axis. All right, I will see you in the other videos.